Hello everyone, now we're going to study the second part in this section, which is tangential and normal component of acceleration. So firstly, let's take a look at the graph. If we have a particle moving along a curve like RT, and we know at any point we can find a tangent vector like t, right? And also we learned the normal vector, which is perpendicular to the t vector, which is n vector. And we are going to find, the acceleration in those two directions. Okay, so it's like, for example, we are going to find AT and AN. So it's like a component. So what's the acceleration in the tangent direction? What's the acceleration in the normal direction? Now let's take a look at have a quick review of tangent vector and the normal vector. So the tangent vector equals what? We know that is the derivative of the r, right? And which is r prime. And because it's unit vector, we divide by the length of this r prime vector. And this is tangent vector. And let's see what is normal vector. Normal vector we just learned, which is t prime over this. Okay, because normal vector is perpendicular to the derivative itself, derivative of the tangent vector. So we learned those two before. Now let's take a look at acceleration. Acceleration equals what? Okay, so acceleration A equals dv dt. And what is dv? V vector is the derivative, r is like a v vector is dr dt. Actually, that's a velocity vector, right? Okay. And we are going to write down this as this way, okay? Newton's notation. So what is the vector v? So vector v, actually we can also write down here like v over length of v. So it's just another way to write down the tangent vector. Is that right? Because r prime is v. And from here we can say v vector equals v length times t. So we are going to write down this way, v length times t. And next, we're going to use product rule, which is v length derivative times t plus v times t prime. Okay, so this is the acceleration equals this one. So you can see now it's combination of something times t, and we can say this is like a component in t direction. So this is component in t direction. And then right now we want to change this into something times n, and that will be the normal direction component. Okay, that's what we want to do. So think about the vector. So the vector equals 3i plus 4j. This means i's component and j's component, they are 3 and 4 respectively, right? So if we want to write down a vector as, for example, 3t plus 4n. So component in the tangent direction and the component in the n direction. So that's what we want to do. Okay, now let's take a look at how to change the second term into something times n vector. Okay, and if we look at the n vector, n, which is t prime over t prime length. Okay, now I'm going to write down this one. I'm going to write down curvature. Let's think about the curvature. K equals what? curvature has the length of t prime. I'm going to write down. In the formula I give to you is r prime, actually, the length, but r prime is same as v vector. T prime length. Okay, and from here we can find t prime length equals curvature times v vector. Let's write down the n vector. N vector is t prime over t prime length because it is unit vector. So t prime equals n vector times t prime length, and t prime length is here. So let's write down n times curvature times the v length. Okay, so that's the t prime. Now we are going to substitute this into the t prime there. So let's see. Our a vector equals what? V length prime t plus v length t prime becomes n vector curvature v length. And we are going to rewrite the second term a little bit. So v prime order. So just organize the order of those two terms. K curvature and the v vector length square times n vector. And now we define this to be the t's component, at plus an times n. And what is at? So at here equals v length derivative, and an equals curvature times v length square. So that's the component for the acceleration in the tangent direction and normal direction. Okay, so now let me give you the definition. Definition 1. If the acceleration vector is written as this one. Okay, a vector equals at t plus an n vector. Then what is at? At equals this one. The length derivative, actually, let's rewrite length derivative plus and an equals k v square. And they are tangential and normal scalar component of the acceleration. Okay. Tangential and normal. This means what's the acceleration in those two directions. Component of acceleration. Okay, so now if we look at the an and the at, so the at is okay, it's easy to calculate because for the at, we can calculate the velocity easily and the length, and we can just take the derivative, right? But an looks complicated because we need to calculate curvature. That's a big calculation. But right now we have a formula, easy formula for us to calculate an. So let's take a look. We're going to do this way. If we just take a look at a vector and we take the length of the a vector, that's the acceleration vector, and the square of it, and we know this is like a dot a. We proved this before, right? So this is like a a1 square plus a2 square plus and an square, and all the an, they are just like a component of the vector a. So that is the length square, a dot a. And right now we are going to write down a as att plus an dot ATT plus ANN. Okay, let's perform this product. And this give us what? This give us actually AT square times T dot T, right? And here AT, AN, they both are scalar, so just like constant, treat them as constant, and use this term times that, which is AT, AN, T dot N, and plus use this term times everything here, AN, AT, N dot T plus AN square and N dot N. Now let's take a look at T dot T, T dot N, and N dot N equals what? Okay, T dot T. T dot T is T length square. Is that right? And what is T? T is unit tangent vector. So because it's a unit vector, the length of T is 1. And the same thing here, N length square, which is also 1. And how about T and N? T is here, N is there, they are perpendicular, so the dot product of two perpendicular vectors, dot product 0. So actually, this term and that term, N dot T, T dot N, they both equals 0. And this term equals 1, that's 1 equals 1. So actually, we get A length square equals what? AT square plus AN square, and if we simplify, and AN equals root of A length square minus AT square. So that means if we know AT, if we know the component in the tangential direction, then we can find this component in normal direction. Okay, so this is given by the formula. In the future, we can always use this formula to calculate AN. So you can see, for a given problem, the most important part, calculate A, and then calculate AT. And also we need the length of A, and just use the formula, we can find all the components. Now let's take a look at the example. Example number, let's take a look at the number, I think choose 3. Yeah. Now, without finding T and N, so that means we don't need to find the tangent vector and the normal vector, so write the acceleration of the motion. The component of the solution. Of the motion. And the motion is given by this one, RT. Cosine T plus T sine Ti. Sine T minus T cosine Tj. Okay, so firstly, let's take a look at this RT. What we are going to find, actually we want to find AT and AN. And here we don't need to, without finding the tangent vector and normal vector, so we are not going to find the T and N. We just want to use the formula to find the AT, AN. So firstly, we need to find it. For AT, what that equals to? Length vector derivative, right? So firstly, let's find the V vector. So V vector, which is derivative of this RT. I'm going to write down the component form. Okay, I prefer this way. So cosine T, just take the derivative of the R. So negative sine T plus sine T plus T cosine T, product rule for T sine T. here. And then this one, cosine t minus cosine t actually here derivatives minus like a cosine t plus t cosine t derivative, so minus t sine t, and then when we open the parentheses, so plus t sine t, right? And then cancel. So here's just a derivative. This is pretty easy. Just be careful. T sine t. This is v vector. Now let's find the length of the v vector. The length of that one should be t squared cosine square t, t squared sine square t. If we combine them, you can see t squared cosine square plus sine square, and which is 1. This equals 1. So which is root of t square, which is just t. And what's the derivative of this one? It's just 1. And so we find our AT, which is 1. Right? AT is just the length of v vector derivative. Next, we want to find AN by using the formula A length square minus AT square. This is already known, so we just need to find A vector length. Okay, so v vector, how to find the A vector? We take the derivative of v vector. So let's write down, I can write down more detail here. V vector derivative. And now we look at our v vector. Where's our v vector? T cosine t, t sine t. Take the derivative of that one. Product rule. So cosine t minus t sine t. Derivative of t sine t should be sine t plus t cosine t. Right? And next we calculate the length of A vector. Looks complicated, but you know we can cancel a lot of terms later. Square plus sine t cosine t square. Simplify. Cosine square t, expand the square thing, and minus 2t sine t cosine t plus t square sine square t. That's the first term, right? Expand the first term. Second term, sine square t, 2t sine t cosine t, t square cosine t. Looks long, but you know, here we can cancel the 2t sine t cosine t and the negative sine t, 2t sine t cosine t. We cancel them, and we can combine this and this into 1. Is that right? And here we can combine those two into t squared. So it becomes 1 plus t squared. Okay, that is A length. And what we need in the formula, actually we need the length of A squared. So let's write down here. Square root of, here's the formula, minus AT squared. This is the formula for the AN, right? And now square of the length of A, which is 1 plus t squared, and then minus AT. AT is 1 square, so it's still 1. And when we cancel them, which is t squared, t. So you can see, even this look complicated, but after simplify, our AN is pretty easy. So now let's write down our A. That is AT times T plus AN times N, which is 1 times T and T times N. So we can find tangential and normal component acceleration. Right, that's the answer. Let's see, I'm going to give you one exercise. It's just extra practice, you know, for finding the tangential and normal component of acceleration. And RT is given. rt minus 2j minus 3tk. Okay, this is rt. This is in 3D. That's okay, we just follow the same procedure. And then we can find everything. This is the first one. Actually, this is a line, so it's going to be 0, all the zeros. And the second problem is a little bit better, and let's try the second one. Cosine ti a sine tj btk. Usually for something like a turn, they have like a normal acceleration, tangential acceleration, right? Like when you drive on the road, we always have acceleration inside. That's why keep us on the road. If we have the inside acceleration, so we can always stay safe. Now let's take a look at the second problem. I'm going to give you the solution. If we look at the RT, the motion actually is helix, right? Because z is bt, increasing with t. And x and y satisfy a circle, and circle has radius a. Okay, so let's take a look at how to find at. So at definitely is going to be v vector and the derivative. So first step, let's find the v vector. I'm going to write down this way. Okay, negative a sine t. That's the derivative of r, right? Cosine t, and here b. And the length of v vector, which is root of a squared sine squared, a squared cosine squared, plus b squared after simplify. So we did this a lot. We combine that sine squared cosine squared becomes a squared plus b squared. And if we take the derivative, we noticed that there is no t, right? So actually this is constant. And then what is v prime t? V prime t just equals derivative of the constant is 0. That is a at. So this is at. Next, we are going to find the an. So in order to find the an, we need to find the length of the a vector. So now I'm going to find the a vector. That's the derivative of v vector. So now I'm looking at the v vector. Negative a cosine t, negative a sine t. Derivative of b is 0. And the length of a, which is root of a squared cosine squared, a squared sine squared, and plus 0 squared is just 0. So it's going to be a. Now let's take a look at our formula. It is going to be a length squared minus at squared, right? So it's going to be a squared minus at is 0 for this problem, so which is just a. So in our case, our acceleration equals 0 times t plus component in n direction times n. So actually it's just a times n. That means what? If you think about helix, what the helix look like? Look like this way, right? And here is a circle. It only has acceleration inside acceleration. So a n equals a, and there's no side acceleration, no tangential acceleration. Otherwise, it will go it will go out. It's not like if like this way, that means it has tangential acceleration. But it's always turned back into a circle. It's going to be just, if we just look at from the top, it's going to run like this way. Okay, so there's no tangential acceleration. It only has inside like a normal acceleration. Okay. And this is the application, of the acceleration and acceleration components. It's pretty important and a lot of useful application in physics and engineering. And we can stop here. And that's everything about this section. In this section, we learned the projectile motion and also tangential and normal acceleration component. So they are not difficult. Some formulas will be given. I'm going to give you the review on Monday and let you know what formula will be given and what will be covered in the final exam. Okay, we can start here.